Hello, I'm Joe Chamberlain, the Executive Director of the Coastside Land Trust. We're delighted to have you with us today for a wonderful presentation on the weather of San Mateo Coast from seashore to skyline. Before we start our webinar, I have a couple of little housekeeping things to share with you. All of our webinars are recorded and they are on our website, so you can visit them. There are several there now, and they're excellent. Everything from marine mammals and birds, plants, and we're coming up on a few more webinars that are going to be quite interesting. Raptor migration at wave crest, sea level rise, bats, and of course a year-end wrap-up of the work we've done. After the recording today, there will be a email sent to all of you that that covers today's webinar so that you can link into it. Also, if there are additional questions, we will deal with them. The plan is that Kate Dickey will do a Q&A at the end of Jan's presentation, and hopefully we'll get through all of the questions. If not, we will do a follow-up and make sure that that we've shared all the information from our expert, Jan Null. Jan is quite a famous person. He's been with the National Weather Service for almost a quarter of a century, he tells us. And then as a professor of meteorology at San Jose State and San Francisco State for another almost quarter of a decade. He brings incredible passion and expertise to this subject, and we are delighted for a couple of things. Number one, to have him with us today, and especially that he lives here in our community and is a member of our community and our family. So with that, Jan, would you like to share any more details about yourself and get going here?
Sure. Thank you very much, Joe, and everyone. Thanks for joining in today. Good example of some June gloom after some nice weather. So maybe all settle in with an extra cup of coffee, and spend about the next hour talking about the weather that's all around us. Some of the reasons it happens, the things that we experience every day. Hopefully, I can bring you some insights into those. I should mention that this is condensed down a lot from a Meteorology 101 class, from about 60 hours of material down to about an hour. So we're going to go through fairly rapidly, and we'll decide at the end if there's going to be a pop quiz or not. So sort of the quick and dirty outline here. I'm going to basically talk about basic meteorology principles for about 3 minutes. Then I'm going to walk through some of the seasons, the marine layer that we have in the summertime, our dry offshore winds and fire danger in the fall, where and how it rains in the wintertime, and talk a little bit about the green flash, and then walk through some of the things that are on the Half Moon Bay weather page that I put together about a year ago. So Meteorology 101 in 3 minutes. Air is a fluid. It acts as a fluid. If any of you have watched the straightest coming over the hill at Crystal Springs, how it cascades down, you can see the waves in it. You can see it being channeled along Highway 92 there. All the rules of fluid dynamics that we expect in the water also occur in the air. It always flows from high to low pressure, just like water flows from a higher point to a lower point. Warm air, because it is lighter than cold or denser air, rises. As it rises, then it begins to cool as it goes up in the atmosphere. And that cooling can cause condensation and going into the condensation into clouds, or even into larger condensation droplets of precipitation. Sinking air is the The opposite, that air, as it comes down from a higher elevation down to the surface, it warms by compression. It actually, for each 1,000 feet it comes down, it warms by about 5 degrees. That warming also causes evaporation. So if we are having downslope winds coming from skyline down toward the coast, that's air that's drying out and warming up. So again, that rising air cools, condensation occurs, and we get clouds and precipitation. Sinking air, it warms by compression, it dries out. The two biggest influences on the San Mateo coastal weather are, one, that big puddle we have next door to us, the Pacific Ocean. It stays at a relatively constant temperature year round. It's a great source of moisture for the fog, for clouds that form precipitation. And then our terrain, we go from sea level up to a couple 1,000 feet up along skyline, higher than that as we go on south. That terrain blocks the flow of marine air getting farther inland. It channels it through the various corridors to the north, for example, through the San Bruno Gap. That's actually why San Francisco Airport is where it is. That sea breeze is directed through the San Bruno Gap and right at runways 27 left and right. That flow is enhanced as it squeezed down through those canyons and valleys, those low points. The terrain also provides lift. So when that air is moving in off the ocean, it gets lifted up just as if it were rising as warm air, and condensation can occur. So let's talk about summer on the coast. All of our great little sayings here: May gray, June gloom, no sky July, and Fogust. We've actually had a pretty good run so far in June with having some really nice days here. I'll show a slide in a couple of minutes about the contrast we've had between us and those people over in the hotter hinterlands. So the big controlling influence is the Pacific High. Extends from off our coast all the way up into the Gulf of Alaska. This is, in summertime, is the semi-permanent feature that is controlling what's going on for us. Over the land, we get what's called a thermal low. The air is heated up, and as it warms, it becomes lighter, so we get an area of low pressure. And again, keep thinking about that air flowing from high pressure down toward low pressure. The Pacific High also controls the currents in the oceans. All the semi-permanent areas of high and low pressure. In our case, the California current brings cooler water down along our coast. The winds blowing from the Pacific High offshore down along our coast parallel the coast with some deviation inland. But due to the rotation of the Earth, and I'm going to skip the whole hour lecture about Coriolis force, but the Coriolis force causes what's called the Ekman spiral right along shore. The surface water moves offshore, and colder water upwells from the lower surfaces. One of the reasons that we have temperatures along our coast that are most of the year in the middle 50s, unlike other parts of the world. If we go to the East Coast, the Bermuda High brings water up from the south, and that's the Gulf Stream and that warm water on the East Coast beaches. Here are the average sea surface temperatures in summertime along the California coast. You can see it's right down here in probably around 53, 54 degree water on the average. The entire coast and on up through Oregon and down to Point Conception is well into the 50s. Water off Seattle is almost 10 degrees warmer than it is over San Francisco in the summertime. So let's talk about, we have our cold water offshore that gives us higher pressure. And we get warming on the inland areas. Going to be about 95 today in Sacramento. So we have our 58-degree water as of what I looked at a couple of days ago. And again, that air flows from high pressure to low pressure. So we're now bringing that cool marine air, we're bringing it inland over the coast, over and around the coastal ranges, and on in toward the interior of the state. That warmed air becomes lighter, it rises. The atmosphere gets a little taller. We get an area of high pressure aloft, and we get a return flow. So our sea breeze is actually a big loop of air with the strongest portion of that, though, near the surface, blowing from the Pacific on in toward the interior valleys of California. That pattern gives us two different types of fog. One, like we have today, is advection fog. So that's when the wind is blowing over that cold water. We have all that moist air from over the Pacific. The cold water cools it down to the dew point, or the point where you start having condensation, and we get our clouds forming over the coastal water. And then the sea breeze we just talked about brings those clouds onshore. Here's a satellite picture from last evening. We can see that some low clouds are I'm sorry, this was from a couple days ago. This is before the last hot spell. But we can see the stratus and low clouds hugging the entire coast. You can see it extending, for example, up through the Golden Gate, sort of pushing in toward the Berkeley area. We also get some upslope fog. So again, that moist air, even if it hasn't gotten to the point where you get condensation down over the water, as that air encounters the coast range and starts going up toward the hills, it's lifted up into a cooler environment, so that air cools off. You get condensation occurring, and you get the formation of upslope fog. There'll be some days when it will be relatively clear right at the coast, but if we look up along the hills to our east, you can see in the afternoon the areas of that upslope fog beginning, and then it gradually, as the air gets cooler and moister through the afternoon and evening, then it sort of backfills over the coastal plain. And this is an example of that. Not a large amount of fog over the Pacific, but you can see it being lifted up over the coast range. So there is, as we talk about global warming, climate change, we need to sort of think about, okay, what impact is that going to have on coastal fog? How much warmer are the oceans going to be that they're going to impact the formation? Will there be more or less differential heating between that 95-degree temperature that we saw in Sacramento versus what we have over the coast? Is that going to lead to less sea breeze, or is it going to lead to more sea breeze? Is the differential greater inland? If there is a decrease in the coastal low clouds, what impacts will that have on the coastal flora? The redwoods along the California coast get a large portion of their moisture from the coastal fog and from fog drip. And then, will this lack of moisture, will it lead to an increase in fire danger, along with just the atmosphere itself, not even looking at just the coastal fog element? So lots of players going on. All of them have some global warming DNA in them. It will be figuring out which scenarios are going to impact these areas the most. I put together a quick graph of the summertime maximum temperatures in Half Moon Bay. And if we look back at the beginning of this is around 1950 here. The orange line are 10-year average max temperatures. sort of a lull in the 50s, and then this gradual increase. If we were to put a trend line, you can see that it's going up. So over the last almost 20 years, we've been up at these average summertime high has been almost at 65 degrees. Where back in this area, it was down about 63. So it's certainly definitely a trend for there to be our warmer atmosphere. We're also seeing the same trend in the minimum temperatures, not quite as dramatic, but certainly is it certainly is happening. Though if we have less in the way of coastal stratus, that means we're going to have more radiation cooling at night. We all know, when we get up on those mornings when we don't have the fog, that it is definitely, those mornings are cooler. So will there be some feedback mechanisms that cause these things to counterbalance one another? This was a case from 2 days ago, and there is a weather reporting station right at the south end of Main Street, right by the fire station, and then another one over at the PG&E yard that is at the junction of 92 and 280, and it's only 6.5 miles as the crow flies. A lot longer with weekend traffic, but we don't need to talk about that. But there was on Thursday, there was a 34-degree difference between those 2 points. Normally that difference is more on the order of about 10 degrees. So really an extreme case, about as much temperature difference as you can get in a short distance. Let's move on into autumn. This is when we start seeing the Pacific high is less dominant. We start seeing more in the way of offshore winds with high pressure inland instead of off the coast. That is also at the time of year when we basically have gone from typically May or even late April this year on until we get into the first storms, most often in about mid-October. So we have the forests and the grasslands are at their driest point of the year. We have these offshore winds, which are downslope, like I said earlier. And so you have, those are causing more moisture to evaporate. So the fuels are at the driest point of year. And then we also have the threat, as we saw last year, of occasional lightning sieges as we get subtropical moisture from hurricanes and tropical storms off the Mexican coast, working up toward California. The scenario that most often leads to these offshore winds is when we get high pressure up over the Great Basin. Those winds are called Diablo winds as they blow over the Diablo range and then on into the Coast Range. Southern California, they're called Santa Ana winds, and on down blowing into the Gulf of California and Baja, they're El Norte winds. So here's a quick little schematic. Again, we get clockwise flow around areas of high pressure. We get this downslope flow over the Sierras and then over the Coast Range and the Diablo Range. When that area is enhanced by an area of the jet stream aloft, that's when we get the strongest of these offshore winds. Here's a little cut and slice view with that warming and drying first initially over the Sierra. Again, going from the Great Basin is typically about 4,000 feet. Bringing it down to close to sea level is about a 20 degrees rise in temperature just due to that compressional heating. Dries out and warms up even more as it comes over the Coast Range and the Diablo Range on down toward the coast. The strongest of these winds are over the ridges of the Diablo Range and north the Mayacamas Range up to the east of the Napa Valley. And the flow is broken up a little bit so that our wind speeds over along Skyline, for example, are not as strong as are seen normally over the higher mountains that are to the east. This is our current fuel threat level. This is looking at the moisture values of coyote brush up along Skyline. There's a sampling point up near Skyline in 92. On June 1st, those values were right at the lowest that they've ever been. The blue line here is the 2021 values. The red line is the lowest ever, and the little crosshatches are the average values. So things are already very dry in those areas, carry over from our very dry winter. Just a couple quick slides about last August. This was a satellite image showing lightning data from 5 a.m. that last August 16th. Extensive area right off of our coast, as well as in over the East Bay and several more areas offshore. This was a picture I took in my backyard here in Half Moon Bay. Certainly as dramatic a lightning siege as I have seen, but these happen about once a decade. Every 10 years or so, there will be a surge of moisture from the subtropics get lifted up in just the right configuration that it produces lightning as it moves in over California. This is all the result of former tropical storm Fausto. And this is the oh wow slide. These are the 1,026 lightning strikes that occurred in the PG&E service area on the morning of August 6th. And you can certainly see this large concentration coming down over San Mateo County and then on into Santa Cruz County, resulting in the CZU fire complex. And this was 2 days later, looking to the southeast from Pigeon Point Lighthouse back across at the CZU complex fires. Well, let's get out of fall and back to some cooler weather and some rain. So we are, most of our rain comes from Pacific cold fronts. You will hear in the media a lot of terminology calling them atmospheric rivers. Those are just the intense cold fronts. Same mechanism we've always had. Atmospheric rivers are not anything new. They get orographic lift, so the terrain is lifting up these cold fronts as they come up over the coast range. The terrain providing additional updrafts. Those updrafts push that cool moist air even higher, so it gets colder. And you get more precipitation the higher up it gets. And so you have the maximum precipitation occurs along up along the crest, for example, near here, Skyline, and then on down into the Santa Cruz Mountains. On the east side, or the lee side for us, is when there's actually a rain shadow. So we see a decrease in the amount of rainfall. So just like in the wintertime with the Pacific High up here in the Gulf of Alaska and the Bering Sea, Pacific High is now sort of a non-entity as far as controlling much weather for us. It's primarily south of California, and the Aleutian low takes over. And this, combined with the jet stream, spins off the cold fronts, those barriers of cold air moving in and getting lifted up by the cold frontal process itself, as well as being lifted up by the terrain. So as that moisture moves upslope, we get an increase in rainfall, and then that sinking air, again, sinking and drying air, we get a decrease in the amount of rain. Oftentimes there is some rain on this side, but it's significantly less. There is, if going a little bit farther south, there is a point in the Santa Cruz Mountains that gets about 60 inches of rain a year up near Ben Lomond. If we go to San Jose Airport, which is just over 16 miles away, they get 15 inches of rain. So a factor of 4 to 1 as far as the upslope rainfall. This is one of my favorite graphics from the textbook that I have used for years, showing if we take a slice of the terrain from the coast on into the deserts of Nevada, and if we look at the annual average rainfall for these locations, you can see how here's the Santa Cruz Mountains impact the amount of rainfall. It goes up, it drops down as you go across Santa Clara Valley, up over Mount Hamilton, drops back down over the San Joaquin Valley, and then as you go on up in the Sierra, it reaches its maximum, and then it drops down to very little precipitation left over by the time it gets into Nevada. And these are all fairly unique patterns. You don't see these sorts of contrasts in a lot of places. And again, it's the influence of having the Pacific Ocean right next to fairly steep terrain. This map shows the average annual rainfall as we go along our San Mateo Coast, as well, and then another line of data points up here along Skyline. This one up here, this 37, is Montera Mountain. So you can see that again, that upslope influences going from 25 to 37 inches in a fairly short distance. The average here in Half Moon Bay is about 29 inches. Up around Skyline, it's 32. So we go farther south into the higher terrain, we get even larger amounts and larger differences. So quite very large contrast that we see. I didn't plot any of the data over here into these portions of San Mateo County, but these numbers are well down into the mid and low 20s. Our rainfall patterns here are unique. You go to most parts of the country, they get fairly equal amounts of rainfall in the summertime as they do in the wintertime. They're getting colder continental storms that don't have as much moisture as storms coming off the Pacific. Here in our Mediterranean climate, which is only about 2% of the world has a Mediterranean climate, we are characterized by these periods from May on through the summer months of little or no rainfall. Actually, the textbook definition of Mediterranean climate is characterized by summertime drought. So that's when everything is pretty well shut off as far as amounts. And then it ramps up in December, January, and February, and March is still pretty high as far as our rainfall amounts. And these are the monthly amounts for Half Moon Bay. Here's looking back at the last 70 years or so at the seasonal rainfall, and you can see we're down here at one of our low spots. After the average again is here at about 29 inches. So you can see we are down. We have not had an above normal year since 2016 and 17. After the drought period we had from about 2011 through 2015. Take a minute to talk about the green flash. I've been a meteorologist for 47 years. I've always heard about it. I've always looked for it. Until I moved to Half Moon Bay and started photographing sunsets, I had never seen it. And I hear from a lot of people, they have never seen it either. And I've come to the conclusion that the reason for that is that in looking for the green flash, we're staring into the bright sun. And it really decreases the acuity of our eyes to see subtle things, especially a small area of green that is in this case at the top of the setting sun. Here's another recent example. A little bit of green here on top, a lot of miraging. There were some inversions or areas of warm air instead of cold air right over the ocean that gave some of the peculiar shapes here. Nice example of a green flash right on the horizon. This is looking from out along Mavericks. This is a relatively rare example. I happened to be shooting the moon set at Pigeon Point, and it wasn't until I was looking back at my pictures a couple of days later that I noticed here at the top of the moon there was a green flash, and not something that is seen very often, and just really felt fortunate to have grabbed it at the time. You can also see some of the effects here. This is a mock mirage as the moon is setting right before sunrise over the out over the Pacific. Back a little bit over a year ago, I put together a Half Moon Bay weather page. I hope a lot of you have already found it. If not, it's easy to get to. It's at ggweather.com/HMB. I expect to spend the next few minutes just talking about some of the material that is available on that page. And I encourage any of you that know of other sites that would be an enhancement to the page to drop me a note. My emails will be at the end of this presentation, as well as on the Half Moon Bay weather page. So this is what the page looks like. And let's walk through a few of the different sorts of things that are on here. So the Half Moon Bay Airport for current conditions. They take their weather observations every 20 minutes, so you can get a good running feel for what is going on. These were some from about 5:15 this morning, and then going back for several hours prior to that. Temperatures, wind speed, visibility, what the weather conditions were, mist, and overcast at 300 feet. So pretty typical summer morning. Also, I have a link here to the weather from the Half Moon Bay weather buoy. It's offshore about 12 miles or so, and this is the sorts of data we can see the wind speed and gusts, and as well as some of the sea conditions, wave heights for 10.5 feet, information like that for people going offshore. This is one of my go-to weather sites, is interactive observation page. This is just a screen capture, though. This is a page, as you scroll in or zoom in and out on this page, you can get more and more data for lots of weather points. And if you click on them, you get a pop-up box like this. This is from one of the PG&E weather stations that's been put up on power poles around most of northern central California. I think they now have about 2,000 weather stations scattered around. This one is up on Skyline, about a mile south of Highway 92. Drive along, you'll see a wind vane and some other instrumentation at 20 feet above a power pole. Actually, there is another site, the site I showed earlier at Main Street. And then also up here on Higgins Canyon, another one at Miramontes Road. These are also the PG&E sites. Those are the ones that are monitored as far as whether the power shutoff should be initiated. Satellite images. This is a visible satellite image. This is what, if you were up on the GOES satellite at 22,000 feet, be looking down, this is what you would be seeing. This is from a couple days ago with good stretch of stratus along the coast, that sea breeze blowing in through the various low spots in the coast range, here flowing up into Pescadero. There's also at nighttime, there is a fog channel, nighttime physics. And so this is from about 5 o'clock this morning. So you're seeing the white outline here is where the stratus was pushing in through the Golden Gate and on into here. We can see the push up the canyon up toward Highway 92 and some of the other places down Monterey Bay and on into the Salinas Valley. So great way to get an idea before the visible satellite pictures are available, which are again only available after daylight to see what might be going on. These are the days that tell me whether to go back to bed if I want to go out and shoot night photography. I think the best weather forecasts available for the area come from the National Weather Service. I do have a bias, having worked for them for 23 and a half years. But unlike the app on your phone, which just comes from a single computer model that whatever company your provider is, gives you, just an icon like this and a single temperature that comes straight out of their computer. These products have been looked at by a human being, in this case down at the National Weather Service in Monterey. They're looking at a large number of different weather models and combining those together to come up with what they think is going to be the best forecast. This is the top screen, the top page, and then you can get on down. You can get the text version of that with the sky conditions, temperatures, and what the winds are. Obviously, here along the coast, we watch, interact with the waves. I like Storm Surf. I think they have really good graphics showing what wave conditions are, as well as wind and swell conditions, as well as wind and wave directions. And they also have a nice tabular table. This is for Pillar Point with surf size, swells, swell periods. When we start seeing these swell periods up around the 20-second range, that's when we have the most energy coming from the Pacific, and that's when we're going to see the highest impact of waves along the coast, as well as in the winds and the significant wave heights. There's also some climatology here on the site. This is for Half Moon Bay. The top table is for temperatures by month. So the average daily high temperature here in June is 63.9, average min 49.9, and the number of days greater than 90 degrees, 0. You can see some small fraction as we get on into September and October when we get some of those warm offshore winds, but we're much below that. The bottom table is for precipitation, again by month, and about 5 inches in January, 5.17 in December, and again the number of days when you get more than a ½ inch of rain, for example, is 3.5 in an average year in December. So lots of information that you can use. Again, our interactions with the ocean here, the NOAA tide charts, and this page populates with what the current days conditions are, as well as the forecast for the next 48 hours or so. Along with the weather stations that are being put up for monitoring the conditions for winds in the on up in the higher, primarily up in the higher terrain. There's a number of what are called fire alert cameras. This is one that recently has been come online up at the top of Higgins Canyon, and I think it's one of the best overviews of Half Moon Bay. Here's Pillar Point out here, and then on well south of this, and this again from a couple of days ago when we just had that nice clearing inland, but the fog bank was still offshore. So that's the prepared part. I've resisted the urge for a pop-up quiz at the end, but as Joe said, I'd be happy to get some Q&A here.
Right. Thank you so much, Jan. We have a number of good questions here. You'd mentioned that there was a weather textbook that you like, and someone asked again what the title of that is. Sure.
It's Essentials of Meteorology by Don Ahrens, A-H-E-R-N-S. It's a go-to textbook in the country. It's very readable, lots of good graphics. It's the one I've used for 25 years or so.
Well, and we'll add, maybe we'll link that in the follow-up email as well, so people can order that.
It's a wonderful resource.
So Maria asked, why are there strong winds right at the beach and then much less just inland, just a little inland?
A lot of strong winds at the beach are influenced, especially as it comes up over the bluffs and around the terrains, like around Pillar Point, around the airport, where, again, going back to areas of fluid, it gets compressed as it goes up over those areas. And so just like if we put our thumb over our garden hose, it causes a faster stream. The Venturi effect, Bernoulli effect, lots of names for it, increases the speeds in those areas.
And actually, Kristen asked, so it's sort of that same idea, is that if warm air sinks and warms by compression, doesn't it make it denser, making it sink more, not less dense? As you said, warm air rises.
Yeah, the air itself is going to be less dense because it's warmer.
A couple people asked about the cause of the green flash.
Yes. So it's the as the light from the setting sun is refracted as it sinks into the air over the ocean, the green light is refracted at a slightly different angle, so it tends to pop out. You also get you get inferior and mock mirages, which also focus that light either above it in the shapes that we saw in some of those pictures. And I can provide a link. There's a wonderful atmospheric optics site that I use on a regular basis if someone really wants to dig down deep into that.
Gary Digg was asking, he was talking about, he had never heard of roll clouds, and then he was doing some photography, and he was observing these approaching roll clouds. And he said when the cloud arrived on shore, when he was photographing, there was an intense blast of wind that blew everything around at the outdoor eating area at the Ritz-Carlton, which is where they were. So his question is, what are the exact conditions that allow roll clouds to form?
It's when you have a stronger wind area right above a stratus layer, and as it comes up over that layer and gets in front of it, it brings some of that cold air down toward the surface, and it causes that frontal edge to begin a rolling process, and so you get that downburst of wind, and they can be fairly significant. There's I've seen small versions here forming off of Pillar Point, and also some down into Monterey Bay around Santa Cruz. And if anyone goes to Australia, there's some areas where they happen very regularly in the Sydney Harbor.
Chip asks, why are the fog and sun patterns not more consistent? Says, for example, often on a day that starts sunny, the fog will start forming over the ocean and move inland, leading one to think that the remainder of the day will be foggy. But then an hour later, the fog is dissipated and it's sunny again. And then yet again, and an additional hour later, the fog is back.
Well, yeah, there's always this competition between the moist marine air and the drier air that's inland. As we get on into the day, the sun is shining and evaporating some of that air that moves farther inland. You get a little bit period of stronger winds. Those clouds can push farther inland before they get evaporated, and so it's this sort of this tug of war between where that boundary is going to be.
And Steve Mahler asks, how can I best read the tide and surf charts to predict the best time for tide pooling?
Well, the best times are going to be around the full moon and the new moon. And so, if we check, our tables for those, that's when we have the strongest gravitational pull, and you're going to have the lowest tide. So you want to look for those dips in that chart that I showed when it's down into the minus category. So those minus tides are when you have the biggest amount of tide pool is exposed.
Let's see. Linda's asking, what caused the strange rainbow occurrence the other day?
Although, yeah, I saw some of that. I forget if it was on Facebook or Nextdoor, but there were some iridescent clouds. So there was a regular rainbow is formed as with the light source behind you, the sun, being refracted and reflected inside raindrops and coming back to you as a spread of light. Well, that can happen in other clouds too. This was a band of clouds higher up in the atmosphere. There wasn't any rain with them, but just the sun and the clouds were just at the right angles that you had that same refraction of light into the rainbow of colors.
Thank you. Sarah asks, our fog has diminished considerably over the years that I've lived here. I assume that's because of climate change. Will it ever come back, or are we out of luck?
I don't have an answer for that. There are, again, I sort of mentioned a little bit about some of the feedback mechanisms. There are some studies being done looking at satellite imagery by the USGS. They have most of the period from 2000 to 2010 mapped, sort of waiting to get some of the data for the last decade to see how extensive those changes in fog patterns are. And again, it's going to depend. There's lots of moving parts here, as we've seen with just what causes the formation of the fog, and which one of those of that tug of war is going to end up being stronger. There's probably going to be a split vote between people that want more sun or more fog.
When you were showing that incredible slide from August 16th, what created such unusual conditions for the lightning siege of August 16th, 2020?
Yeah, it was this pulse of moisture coming up from the subtropics. Most of our storms that come from the North Pacific are cold. They don't hold nearly as much moisture as that warm tropical air coming up. And that area encountered an area of low pressure, which allowed for some additional rising air. So we're taking all that rising tropical moisture, and we're basically end up with the sorts of weather that you would have, 1,000 miles to the south in the tropics, with heavy downpours and with all the lightning.
Michael's asking, how do you define low pressure and high pressure in terms of air molecules?
So there's lots of complicated answers, but basically it's the weight of those air molecules that are above you. What your barometer is measuring is basically what the weight is of all the air molecules from where you are all the way up to the top of the atmosphere. And so areas where you have more molecules in that distance or higher pressure, and areas where you have less or lower pressure. And again, the factors that are influencing those is the heating and then what the density is of those molecules.
The question here is, it seems that Pacifica through Half Moon Bay is foggier than the areas in the south of the coast. And why is that? If we're all on the coast, why are these different levels of fog present? And then also someone there's an additional one, which sort of could be connected with that, is why does the marine layer kind of pull away from the coast just south of Pigeon Point?
So as far as the first part, to the farther north, where we have the Pillar Point Ridge, so that causes some additional uplift, so you get more in the way of fog forming in that area. You have up around the Devil's Slide, Mount Montera area, where the higher terrain is closer to the coast, so those are going to tend to be foggier areas. And moving on down the coast with the different changes in terrain, where the coast sort of dips back to the east a little bit about Año Nuevo, the areas south of Pigeon Point, and so you're kind of out of the flow quite as much, so they aren't going to have quite as much fog in those areas. So yeah, we have these little culls, if you will, as you go up and down the coast where you have differences.
And Lawrence and Bonnie asked, will climate change, do you think it's going to bring more tropical weather and lightning? And what do we know about the changes of the incidences of lightning on the coast, particularly as it relates to fire?
I don't think we will see a significant change as far as more tropical air. The differences we are looking at with global warming are on the order of a couple degrees Celsius. That's really not going to change where the boundaries are for the tropical air, bringing them much farther north from where they are now. We have several areas where we have the polar jet stream defines things to the north. There's a subtropical jet stream down near the Mexican border, and those aren't going to shift a significant amount. So I don't think we're going to see probably even a measurable amount of increased lightning activity up in this area.
And about the fire danger slide, was the fire danger last year predicted by the data on that slide that you showed?
No, where the occurrence of of a lightning event like that is somewhat random. I mean, they happen on a once a decade or once every 15-year period. Things come together just right. What is was predictable then, and unfortunately could be predictable this year, are the state of the forest from having very low rainfall years. All the vegetation is extremely dry, like the coyote brush slide that I showed. So, it takes a spark for a fire to occur, of course. But when you have the kindling is already pretty dry, things are more likely to happen.
And with all your years of experience, how accurate do you think that weather forecasting is? And what do you think when you look at the future?
Well, it has gotten more accurate, and the metrics that I usually look at is, okay, how far in advance can we predict, let's say, that it's going to rain? When I started working for the National Weather Service in the mid-1970s, about a 3-day forecast was about as far out as you could make a relatively reliable forecast. Okay, it's going to rain in Half Moon Bay. Each decade since then, so over the last 4.5 decades, we have improved that by about a day. So we now out about 7 days that we can have a pretty good idea of whether it's going to rain. on out at a week. So instead of 3 days, we're now out at 7 days. So that, that's one metric of accuracy on, as far as temperatures, and even short-term rain forecasts, those have all improved. But if you're forecasting whether it's going to be a 66-degree day or 67-degree day, doesn't really impact a whole lot. It's those big changes, and those are caught almost all the time now.
Thank you. And this Lawrence is asking, why is it windy at the interface of the expanding fog?
I'd have to think a little bit more about that. Have him send me an email.
That sounds great. Let's see, maybe just a couple more questions. Can you just talk again a little bit about why the month of May is windy as opposed to the winds in autumn, as opposed to why?
Sure. Again, it's all driven by our areas of differential heating, where the ocean is cool with higher pressure, and then the inland areas are warmer with lower pressure. So as we're getting on into May and June, we start seeing those bigger temperature differences, and those are exacerbated by the fact we have the Pacific high, not only just the nearshore high pressure due to the upwelling and cold water there. As we get on into autumn, the Pacific high lessens, and we start seeing less differential heating between the coast and the inland areas, so that causes the drop off there.
Let's see, maybe, how interesting. How much math do you need to learn to become a meteorologist, and what kind of math?
So to become a meteorologist, it's pretty much the same course load as you would if you were to become a physics major or to go into engineering. So you need basically 2 years of calculus, differential equations, and then a year of chemistry and 2 years of physics as well. And then you add on, lots and lots of meteorology courses.
Those are great questions. Aspiring
Yeah, I like it.
meteorologist. Yeah. So this past winter, there were a couple of nights when the low temperatures in Half Moon Bay were down in the high 30s, unlike the rest of the coast, which was in the low 40s. Is there a geographic reason for this?
Without knowing exactly what they're talking about, but it was probably an area that was more cloud free than another area. That's typically is the big differentiator when it comes to what the temperatures are going to be at night over short distances.
And then Lawrence asked a couple of questions here, and I think how much the ocean temperatures have increased and how much higher the sea level is.
So I think as far as the sea level, I'm going to plug your upcoming webinar about sea level change. That's not something as a meteorologist that I monitor enough that I would speak to it here. The oceans have warmed out in the bulk of the ocean, but where our temperatures here in Half Moon Bay and the San Mateo Coast are more driven by the California current and upwelling. I have not seen a significant change as far as those temperatures.
And then maybe this will be our last one for now. Well, actually, I'll just say that Joanna asked, do you post your awesome photography on your website?
Actually, I don't.
Photography is incredible.
Yeah, it's scattered around social media on the Facebook We Love Half Moon Bay page, our next door. My Twitter account is @ggweather, as is Instagram. So it's kind of, I splatter it all over there to be able to share.
Maybe she's asking you to add that in a kind way. Put that on your website.
Yeah, That is actually my business website. So I try to separate the personal.
Separate the two. Yes. Well, we'll include all of that too in our follow-up email. We got through most of our questions. We have a couple others, and I think these are ones we can add on to the email. Last one though, actually, let's get to this one because this is one that you might want to get to right now. General discussion about thermohaline currents changing in the North Atlantic that could affect weather there. Are there similar North Pacific issues? So
No.
this says, is the difference Greenland?
Yeah, no, we're not going to see that sort of pattern. Where the Atlantic narrows up in the north, it's more of an impact with the flow in and around Greenland. We're not seeing that, or I'm not aware of any studies looking at something similar in the Pacific.
Okay. All right. Well, thank you very much for this presentation. For those of you, I mean, I think you got a good sort of tutorial about the Golden Gate Weather Service website through Half Moon Bay, but this, you got a small taste of it. I would really encourage you to hop on there and check that out, because it gives you so many options to look at the tides and the weather and the marine forecast and those weather cams. I mean, just it really truly is like, if you're gonna, or at least pass that on to people that you know that move to the area, because it's just an orientation to the whole ecosystem here and weather here. So I hadn't heard of it until we met you, Jan, which is embarrassing to me that I didn't know. And then when we met you, I went, how does one live without all of this in one place? You know, you're kind of going all over the place. So it's a huge, huge gift to the community that you've put that together. And to all of you who are here, thank you for being here, and thanks for coming along to this webinar and to learn about our weather. We will have a follow-up email coming in the next couple of days, and that will share with you some links, certainly the recording, and there are a couple of you that we responded to that there would be some questions that we would answer that way. Jan, do you think it's possible to include a copy of your slides in that follow-up email?
Sure. Yep,
okay. So that's great. I think a couple of people asked for that, and I'd love that too. So
yeah, I'll condense them into a PDF that'll be a little more user friendly for everyone.
Thank you very much. So there'll be a follow-up email coming your way. Also, to keep your eyes open, you'll be receiving an email. We work really hard to keep our emails at a minimum coming to your inboxes. So but we have Alvaro Jaramillo will be coming in August 7th. So that's about the raptor migration. We also have in September, as Jan mentioned, a sea level rise presentation that I think it seemed like a lot of the questions that were coming here are people that would be very interested in that as well. I think a lot of us have a lot of questions around that. So we're still solidifying the date on that, but it will be in mid-September. And for those of you who have donated, thank you to the organization. You know that this, of course, we operate completely on donation, and that the funding to support the important land preservation and stewardship and these types of community webinars is critical, and it comes from the generosity of the folks that live here and the generosity of folks who come to present as well. So it takes our whole village to preserve this land and take care of this incredible place we live, and to share and learn about it together. So thank you very much. Thank you, Jan, and thank you to all of you who have joined us. And we will see you all again. Now we won't be together in July, but in August. We'll see you in a couple of months. All right, bye-bye.